familiar if you're doing clustering, and might have come as a bit of a surprise when we started talking about this. So previously, what did we do? Can someone fill me in? What did we do last time?
Quebec-Leibler divergence.
Sorry?
The divergence.
Okay, now you're just throwing random words out. That is true. The word was that phrase was mentioned in the lecture.
Yes, it was.
I don't think the whole lecture was about Quebec-Leibler divergences. I think it was about more than that.
Clustering and information theory.
Okay, good. Clustering information theory. So what are the key concepts you need to understand? See, normally I do this every lecture. In this class, I have not done this much. Let's see how much you remember from last time. So, well.
Huffman coding, KL divergence.
Okay, now you're also throwing out words. I don't want words, I want the story. Anyone?
We can try to look at clustering as condensing information.
Good. Okay, so the basic idea is clustering as condensing information. Okay.
And then the
excellent. Today you're on time, so I'm very happy.
Oh, sorry.
And then some of the tools that we have to work with is like we know about Huffman coding, so like what are the relationships between, like how does information compression in that relate?
So I'm interested in, it's interesting that you're all bringing up Huffman coding, whereas to me, my mind, Huffman coding was not a relevant part of the whole lecture at all. So when you say Huffman coding, what are you thinking of really?
You just used it as kind of the example of like this is how you look at the information stored and how it compresses it, and then
right. So in other words, Huffman coding is an existence proof that
it was the easy example for what we're
that's
trying
right,
to apply.
because it gives you a way to say, okay, look, I can actually compress information down to a certain number of bits. So entropy is actually a good way to measure that.
Yeah.
Right. So that was so we introduced the idea of entropy, and I'm not going to write out the big definitions here, but hopefully you remember what they are. So entropy of a random variable. And what is the other key concept we needed along with the entropy of a random variable?
Mutual information.
Okay, so someone other than Nick remembers what we did last time? Anyone? Mutual information. See, give a clue. What do we want to say about mutual information?
I'm not being graded, so I'm not being graded, so I can stay silent.
Yes, you can. You can also speak up. That's fine, if you wish. You're allowed. Would you like to help us out?
Well, that right there is the entropy.
Yeah. And then mutual information. So we're talking about. So what is how do I even write it? What do I say?
What? Information of X, Y.
Okay, so what is it? What is it trying to capture?
It tries to capture how much another variable explains the other variable given the denominator.
Exactly. So somehow it's capturing the information content shared between X and Y. It's not asymmetric, it's a symmetric notion. So it's one way of saying is, given Y, how much can I learn about X? Or given X, how much can I learn about Y? Right? Okay, so we had these two notions. And then we,
And I was thinking, the way it really is, if you think of X and Y as events, they are random variables.
Yes.
Random, and random variables consist of events.
Yes.
And if you think of Y, it's basically because it's a set, and you look at it as an intersection of sets.
Yes.
And intersection is something that's well defined.
Right, so that's what I did last time actually. So I've drawn this last time. I had this Venn diagram where I said, you could think of the information content of this as h of x, right? The information content of this as h of y, right? And so mutual information was the stuff in the middle.
Yes.
Okay.
At first it wasn't clear to me.
Yeah. That's what So once we had this basic sort of language to speak about information compression, we want to now express the idea of doing clustering. And so we needed a couple of things. We needed to somehow transform our standard notions of, space and quality into the language of information theory. So how did we do that? I must say it's very depressing. It's just 2 days ago.
I don't know how to do that.
Okay, someone else? I'm trying to spread the room.
Sorry, what was the question?
The question was, how did we try to formulate a clustering question using the language of information theory? Suddenly she backs away now.
Thanks for sharing the question.
I see. And here I was foolishly thinking an answer was about to appear. No, but no. Anyone? Anything? So let me start you off by reminding you that there was this notion of T, which is going to represent the clusters, right? And we were going to talk about the assignment of a point to a cluster as represented by some kind of conditional distribution of P of T given X, right? Technically, what I should be writing is P of this random variable to T given that this random variable is equal to X, but in short form, I just wrote it that way, right? And this is some kind of conditional probability, which of course would sum to 1, because you wanted, X to be all of X's mass to be assigned to some cluster or the other. So then, what did we want to say once we have this? Now once we have T and we have X and we have Y, because we said, okay, we're going to think of our data as some kind of matrix where you have X as the objects and you have dimensions which you think of as Y, right? Like an TF-IDF vector or some kind of number of words and documents and so on and so forth. And then we're going to cluster the X's into T's. And then what was the goal here? What did we want to do?
We want the mutual information between the clusters to be small.
What does that formally? What does that mean? The mutual information is you have to give me two parameters. Give me two parameters.
So we're going so that the information between.
Sorry?
Between the mean of clusters?
No.
Between the T's.
Between all pairs of these T's, we want that.
Pairs of T's.
So pairs.
The mutual information is between two variables. Give me two variables. Now there are only three choices of two variables here, so you have 1/3 probability of guessing, but then you try to just guess.
I hope that I want to think about it more than guess.
In fact, you have a half probability because one of them you can eliminate automatically.
So between.
So you can do a Monty Hall probability now. So how do we try to express the notion of space? I mean, the whole point of doing this is say, okay, we can talk about the space required to describe the clustering. How are we trying to capture that in this language?
We should take T's that are as far apart.
That's the intuition, but I want to give you the actual language.
Oh, okay. So
that.
What was it? I mean, you're all frantically scribbling notes whenever I say anything, so I'm surprised you don't have your notes. So what we were saying was that we could capture the space. So okay, think of it this way. Suppose this was a hard clustering, right? So every point was assigned to one cluster or the other, but not ever shared. Then you'd have an actual clustering, and you'd have some number of points in each cluster, right? What did we say was the way to express the space required to describe this cluster? We said that you can describe a collection of clusters in a certain way, right? How many bits would we need to describe that collection of clusters?
we said that if you have K clusters, you would need log K.
In the worst case.
Yes.
But you could be a bit more smart about it.
Yeah.
Right, you could use Huffman
the
coding.
probabilities.
So you could say something like if the fraction of points in one cluster was, pi, then you could think of the entropy of the sizes, right? We'll call this entropy of T. But that's true if all the points were assigned to one cluster, they weren't shared. And so we said, if in fact the correct generalization of this idea when points can be spread across clusters is this mutual information, the mutual information between X and T. And the way you can actually verify this by just saying that, okay, in fact, P of T given X is either 1 or 0, this would actually become equal to that. Okay? So we argued this somehow captured the amount of bits you would need, or the amount of bits you had to describe X given T, in some sense. And you want to make this as small as possible, because you want to have a compact clustering description. And then through a bit of effort, we came across another way of describing, so we said now the quality of the clustering. Now, so we can think of the original quality of the data as the mutual information between X and Y, because that's the amount of information content in the system. And now once you cluster X into T, T is what your data is. It's no longer X, it's T. So the quality is something like I, Ty. Right? And so the goal was to somehow balance these two parameters. And so you want to say we want to optimize some function of ITX, which you want to minimize, minus some Lagrange parameter times IT. Right? And this whole notion came about by thinking of what we call rate distortion theory, and we talked about all this last time, which you have all happily forgotten. Okay, so we said that once you solve this, okay, so now the idea was, okay, what do you do with this? It's a nonlinear sort of optimization, it's a non-convex optimization, you can't really solve it. But actually you can write down the conditions for what any critical solution, so any solution that has a derivative of 0 here would look like. And we said it's going to look like this, right? That you're going to basically have the key variable, probability of t given x, right, is going to be proportional to this times x of minus beta times the KL divergence between the coordinates of x, which is p of y given x, and the coordinates of t, p of y given t. Right? This is our proxy for the coordinates of x and the coordinates of t. Right? And then once you had that, you could write down the other parameters. P of t is equal to sum of p of x, p of t given x, which came from the previous step here. And then once you have that, you can write down the coordinates of y is equal to 1 over p of t, sum of p x y, p of t given x. And so these three system equations will give you this object, which is the unknown, this unknown, this unknown, and this unknown, and they're all related to each other. So you can just, yes.
I have a question. So information gain would be high if the variables are very correlated.
Sure. So, what's your point?
So, and we want to minimize the x of t.
You want to minimize this whole expression?
Yeah, but basically you want to minimize the information.
Yeah, because this is space.
Yeah, which doesn't make any sense now.
Because
The thing is, you have this big space, right? Lots of points, and then you want to have a few clusters.
Yep.
And you want that these t's represent well x's.
Yes.
So if I have a t,
well,
if I have a
that's your representing well the x's is measured by this term, which you want to maximize.
oh no, okay. So what is that?
This is the compression. This is the space required to describe that output. This term here. The number of bits to describe it. This is the quality term.
Yeah. No.
Because t are your new x's. So ity is the new information content. You want the new information content to be
Yes.
as good as the old
Yeah,
information
exactly,
content.
right.
That's why you
So
maximize
what is
it.
in space?
What is the space? The way to think about it, again, the only way to build intuition for this is information theoretically. You have to imagine that you have a channel, okay? And you are basically pushing x through your channel, right? And this is your funnel here, which is compressing things out. And somehow you're reconstructing things from here. And what you want is a channel that is as compressed as possible, but as high fidelity as possible. The channel capacity is controlled by IATX. So you want to funnel your information to as small channel, but you want to reconstruct very well. And that's giving you this.
Yeah, okay. But here the beta is very tricky then.
It's a Lagrange parameter. Yeah. It's the same problem as choosing k,
Yeah.
but it's not really choosing k anymore because k can be left undefined. It's more of a smooth parameter.
Okay,
So it's a little bit nicer.
Okay, now I understand that.
And we'll actually going to talk about beta in a second. I'm just doing a recap.
Thank you.
Okay. So now what we can show is that, and this is basically some basic calculus, you can show that if you differentiate this expression with respect to the main variable ptx, that you set it to 0 as usual, you get these three equations that must be satisfied by your unknowns. Right? That doesn't give us a solution, but it tells them they must have this relationship between each other. And so this gives you an iterative scheme, right? You first guess some values for these, solve for this, then solve for this, then solve for this, then keep going back. Okay? And this basic method, where you sort of start with some random initialization and do this, should remind you of some other algorithms that we've seen. What other algorithms does it remind you of? We have a bunch of equations that are sort of mutually interdependent. They just keep on solving them one by one. What have we seen before that looks like this? What other clustering algorithm have we seen before that looks just like this? Forget the information theory part. The whole idea of a bunch of interrelated variables that we alternate between them. Anyone? The EM algorithm, right? Yes? Do you all remember the EM algorithm? I see major frowns here. Yes? I'm looking at you right there. Yeah. Expectation maximization, K-means. Not getting really depressed now. Should we go back to K-center and start all over again? There'll be more quizzing next week, so be warned. Now's the time to go look at the videos very frantically. So like the EM algorithm and the K-means algorithm that you're all extremely familiar with, this also has a set of interacting equations that they all sort of, you don't actually have a closed form solution, but you can solve them iteratively. Which also means you're not going to get an optimal solution in any sense of the word. You're going to get a local optimum. You can actually show you get a local optimum. But that's all you can hope for. That's sort of such as life when you're dealing with these things. Okay, and this algorithm, this very simple algorithm that just basically says, okay, try to solve these equations over and again for a fixed value of beta, right, is called it's one of many algorithms we're going to see today, called the IIB. I think it's the Iterative Information Bottleneck algorithm. And before I talk more about these algorithms, I want to just sort of tell you what you get as a result of all this, right? So I want to draw some pictures here. So one thing that you can start saying is, okay, I'm going to do this following plot here. Okay. On the x-axis, I'm going to measure the amount of space I need. So I'm going to plot it as ITX. Okay. On the y-axis, I'm going to plot the quality of my result. So it's going to be ITY. Okay? And I'm going to normalize them so they're all between 0 and 1, just to make my plot easier to understand. So what is the maximum value ITX can take? Well, the maximum value this can take is if you put everything in a cluster by itself. And this basically tends towards IXX, right? And IXX is just the entropy of X. So this maximum value of this expression is the entropy of X, so we'll just divide it by that. So you get an entropy. The maximum value of this quantity is IXY. Again, if everything's in a cluster by itself. So so now these numbers are guaranteed to lie between 0 and 1. So we can think of what they look like on the unit square. Okay. So just to make sure we're on the same page here, what is our ideal point in this grid? So again, it's like all these sort of trade-offs between space and quality, right? Where's our ideal spot to be in this square? Where do we want to be? So remember, this is space, and this is quality.
Top left corner?
Top left corner. You want to compress everything down to nothing and have perfect quality. This is the ideal, right? What does this point correspond to here? Right there.
Just no cluster.
Well, we've got 0 space. So what have we done? What kind of clustering does this represent? Everything's in one cluster, right? So this is like everything collapsed into one big blob. What does that point correspond to?
Everything's its own.
Everything is its own. So you remember we talked about these ROC curves and trade-offs between cost and number of clusters? Think of this as another smoother version of that. Okay. Now suppose we actually fixed a value of beta, and we ran the IIB algorithm and we got some answer. Then let's for now pretend this is the right answer. That's going to give us some value of this and that for a particular value of t, right? So there'll be some point in this space, right? And if you did it again for a different value of beta, you might get some other point in the space. And you can show that so let's think of what's going to happen as beta changes. So suppose you put beta equal to 0. What's going to happen?
We're minimizing that.
Yeah, we're minimizing this expression, we put beta equal to 0. If beta equal to 0, we're saying we don't care about quality. Screw the quality. We're just going to talk about space.
Everything's one cluster.
So we're going to end up here. So you can think of this as the beta equal to 0 point. Suppose we put beta equal to infinity, then we're saying all we care about is quality. We don't care about space at all. So this is the beta equal to infinity point. Right? So if you imagine what this plot is going to look like as you vary beta, right, which is not the number of clusters, it's a much more mysterious parameter. It's if you are so inclined, you can think of this as 1 over temperature. It's going to have in a statistical thermodynamic sense, it behaves like 1 over like a cooling parameter. But anyway, If you don't like that, don't worry. You have to be a physicist who likes it. As beta varies from 0 to infinity, you're going to move from here to here. And what you can show is that you're going to move along a kind of concave curve. So you're going to move along something that looks like this. Okay. And again, this curve you should think of as find the optimal solution for any particular value of beta. So any particular point is the solution you get for one value of beta. Of course, I'm saying run the algorithm. The algorithm is not the optimal solution, but let's pretend for now that you're finding the optimal solution, whatever it is. It's going to look like this. And again, this is not surprising that this is basically a Lagrange dual of something. This is what you expect. You had a question?
Should that be dx?
Huh?
Is that xt or dx space?
Does it matter? Visual information, symmetric. Remember, it's the intersection, right?
Yeah.
Okay. So what you get if you plot this for different values of beta, and you can actually do this, you will get a curve that looks like this. And every point along the curve is a particular value of beta. Yes?
Is it guaranteed to be concave, or are there degenerate cases where it's like convex or?
No, it's guaranteed to be concave, basically by the way you've constructed the Lagrange linear. Yeah. And the properties of visual information. And you can imagine different curves. You could imagine for a different data set, your curve might not look like this. Your curve for a different data set might look like this. You could imagine for a different data set, your curve looks like this. So you all hopefully remember the elbow method. To choose K, the elbow. The sharper the elbow, the more, you know. Think of that in reverse here. What you're saying is that this is the ideal point. In some sense, if you can actually have a contour with different values that goes like this, then you're getting a highly clustered data set. Because you're able to keep the space down and still get a pretty good quality cluster. If you get this, on the other hand, you could argue this essentially is random data. That is self-similar. At every step, you get a little bit more for a little bit more, but there's no big bump of any kind. It just goes straight. And in fact, this is one way to calibrate how clusterable your data is, just like we've seen in other cases, right? That the further it is away from this line, the more clusterable it is. And the closer it is to that, in fact, people have used things like measure this distance. Look at the point of slope, 45 degrees. And yes.
It seems like beta should be 1 over the slope of
It is.
wherever you.
That's exactly what it is.
Okay.
Yeah, in this normalized setting. So in fact, you can, because you've normalized this, you can actually say, okay, I will select beta to be exactly the appropriate ratio of h of x divided by ixy, and then you can say, give me that point. And you'll get exactly the point there. In fact, I had, way back when I was working on some of the stuff, we did exactly that. We would say, find the clustering for that point, and then weird things started, cool things started happening to the data. And I'm going to talk about that next. Okay, but yes, that's right. Okay, so let me now erase these things, the extra curves. So I'm just going to go back to our original red curve here. In none of my discussion so far have I talked about the number of clusters. And that's because it doesn't, in some sense, it doesn't matter. One of the attractions of information theory clustering is, yes, you have this trade-off between space and quality, but it's not expressed in terms of the number of clusters. That's an irrelevant parameter. In fact, when you run the IIB, you just throw in like a gazillion clusters to begin with, and just run it, because you have to discretize T somehow. And then somehow the algorithm itself decides, okay, I'm going to focus my energy on like 5 clusters in this run, or 10 or whatever. It doesn't really, it can pick up as many as it needs in some cases. But you can force it to say, I want to use only 5 clusters. And then you start seeing very interesting things happen. If you imagine what's happening to your clustering as you increase beta. What you're basically saying is that as I increase beta, it becomes more and more important to me to maintain quality of my cluster. Okay. So think of my initial, I'm down here, and I have some clustering that looks like this. I have some clustering and everything is one
I
block.
think a better word than saying quality is to maintain the reconstruction, to minimize the reconstruction error. You want to be very good at reconstructing.
But I'm maximizing quality.
Yeah, when you're doing that.
That's why I'm using the word quality, because I want the number to be
Oh,
increasing.
so quality now refers to that. Oh,
Yes.
Yeah, sorry.
Okay, so I have my initial clustering, and all my points are one blob. What is going to happen as beta increases? As beta increases, it's going to become more and more important to me to make sure that if there were two clusters, that they get separated out. It's no longer worth my while to keep them together because this expression is going to penalize me for doing that. And it turns out you can actually see this happening. As you increase beta after some point, say here, you get what is called a bifurcation. Your data set starts splitting into two. And as you increase beta further, it splits into 3, and so on and so forth, all the way to the end. Right? So in some sense, if you remember hierarchical clustering, we were trying to talk about the evolution in sort of backwards order from back there down to here. You can think of a forward direction here, that you have this kind of bifurcation phase change happen. Your data starts off in one phase and it splits into 2 and then more and so forth. And in fact, you could say, suppose I wanted to I want to find the best 2 clustering of my data. Then what would happen is your best 2 clustering will track the original curve up to this point and then will become suboptimal. This is k equal to 2. If we do the same thing for k equal to 3, you would track the curve up to some point where it bifurcated off, and you'd get something else that looks like this. And so on and so forth. So in some sense, this curve is in many ways universal. It captures the entire bifurcation structure of your data. And at any point, you can fork off by fixing the number of clusters and saying it's just getting better and better, but you're never going to get as well as you could have done if you had allowed more clusters. And so this, in some sense, shows you why if you fix a number of clusters in advance, you have this now problem, because now I don't know what's going to happen. The best clustering I get is going to change.
And these jumps are continuous, right? From k to 3.
Well, I mean, I don't know what
for
continuous.
small beta.
Yeah, so you have small, it's at a small transition beta, you have boom. So it's not continuous, it's a bifurcation, right? I mean, so I'm not sure what that means by
Yeah, I mean,
continuous.
like continuous, I mean, like 2, 3, 4. It will not jump from 2 to 4.
That's correct. It might jump, well, it might jump very quickly, right?
Yeah, but it shouldn't, right? I mean,
Well,
there
no,
should be
if you have a degeneracy, right? If you have a degeneracy, it might go from 1 cluster to 4 clusters very quickly because you have a 4-way, essentially, a 0. You know, at that point. If you write down this as optimization, you can have a degenerate set of zeros, right? And you can go from 1 to 4 simultaneously. So you can think of it as continuously going from 1 to 3 to 4 if you want. But in a degenerate case, I can't quite say that. Right? You have to be careful about that statement.
Yeah, I get the point.
I mean, for example, if your data looked like this, right? If you had 4 tightly connected dots, all equidistant from each other and indistinguishable from each other in every other respect, then you'd expect that at some point there's no reason to split from 1 to anything but 4, because they're all identical. There's nothing to distinguish one from the other. So but this is degenerate, which is why I'm saying in degenerate cases you could have a jump, but you can always pretend that it's going through them all the same time. Okay. All right. So this idea is very powerful because this gives you, in some sense, another way to navigate the landscape of clustering, like we did with hierarchical clustering, but going from one cluster upwards instead of going from many clusters downwards. Because now you can kind of smoothly decide where you want to be, and then look at the number of clusters you get there. You don't have to pick the number of clusters ahead. So you still have the smoothing parameter, but it's in a different space now. It's not in the space of number of clusters. It's a much more well-behaved space. It's bifurcation space. And there's been some work on trying to understand clustering through this phase change operation. So you look at the phase changes and then use that to decide the number of clusters you want. And this also gives you another algorithm for doing information theory clustering. You have a question?
It's more from how we sometimes thinks about these problems, since it is not using any matrix.
No, it's not.
It's not using.
Yeah, that's the
so
point.
why, which is your features? Or
Yeah.
They could be any form,
Anything.
categorical.
Absolutely.
yes,
That's the beauty of this, by the way.
Okay, so
Yeah.
that's the case. You don't need to worry about.
That's
mixing
right.
up this.
That's right. I mean, you do have to worry about calibrating different dimensions against each other, right? You don't want, you still don't know how important certain dimensions are, right? There's nothing here saying that. I mean, you might put some prior on y. In fact, you can incorporate that into this expression. You put some probability on y by saying how important various things are. But you have to make that judgment yourself. So it's not completely judgment-free. You do have some kind of prior information you need to put on this. But you're right that you can incorporate heterogeneous data fairly easily in the setting.
And that data could be what we call multicollinear. So data could be, so these dimensions could be
Anything. Yep.
Anything.
You can have. So in fact, some of my work has been, this was a social security number. This was an address. This was someone's name. This was their age. Completely different things. And that's one of the beauties of this method, that you can actually combine different approaches. Yeah, and you don't, one standard approach would be to say, okay, I'll define a separate metric for this column, this one for this, and then try to combine some product metric. But that's kind of, again, a little bit uneasy, because now you have to weight the metrics against each other and scale them appropriately. This you kind of can avoid.
Because currently how we are dealing with this is like probably having separate metric for
Yep,
continuous,
yep,
separate
that's right.
metric for
That's a very standard way to
epilogue,
do it, yeah.
And
Yeah.
then, okay.
But so this is one way to avoid that problem.
Okay.
So maybe I should have said this earlier, right? That one of the attractions of this formulation is precisely that you can handle heterogeneous data much more easily and much more seamlessly in this way. And so these more clunky ways of doing things. Yeah. And that's why it's useful. Okay. So how many of you heard of simulated annealing? Okay, some good fraction of you heard of it, right? So you might be seeing some kind of annealing type sort of thing going on here, right? That you can think of some kind of so the way we think about simulated annealing for optimization is that we have some kind of parameter that controls the temperature of our system. Okay, so the idea is that you have some kind of system with a lot of, local minima and maybe one global minimum somewhere, right? In the beginning, what you want is to say, okay, I have particles at different points in the space, and they're perturbed based on how much energy they have. But the system has a lot of energy to begin with, so they can jump around wherever they want. Okay, they can go everywhere. And I'm going to slowly cool the system down, so that eventually particles get stuck in various basins, right? And they can jump out, but they have less energy to jump out. And eventually, the hope is that if you let them percolate a lot in the beginning and then cool it slowly, you get to a point where you can actually get the global optimum. And there are some sort of proofs that simulated annealing can actually solve an NP-complete problem. The hard part is that the convergence rate, the rate at which you have to cool, gets exponentially slow if you actually want to guarantee that you actually find the global optimum. So it's not like you can solve NP-hard problems with this, or at least it's not clear. Right? It's not a magic wand there. But it is an idea that allows you to do optimization by gradually narrowing the search space. If you think of annealing in the context of this, and remember I said beta should be thought of as 1 over temperature? So if beta is 1 over temperature, what does beta equal to 0? That's an infinitely hot system. Everything can move around everywhere. You have one cluster. As beta increases, your system starts cooling. You don't have the flexibility to jump around wherever you want. And you start falling into these little troughs. You start clustering essentially. In the limit, beta goes to 0, you're at absolute 0, nothing can move. You're trapped in your own little zone all by yourself. So you can think of this whole process of doing information theoretic clustering as a kind of an annealing process. And in fact, there's a particular algorithm now I'll tell you which exploits that idea directly. The idea being that you have to decide at a particular temperature, do you want to split a cluster or not? Right. So in the IIB algorithm, I fix the beta, right? So in the IIB method, I fix beta, it's constant, so I'm really getting 1 point on the curve. But suppose I want to build a move along the curves a little bit. So what you do is, with this other algorithm, which is called DIB, for deterministic IB, because actually it's deterministic. What you do is you have some initial clustering, you have some initial data, and you look at a particular T. So you have some particular T, and you say, okay, I'm going to split this T into two different, into T1 and T2. Right? And the idea is that I have to now describe, so think of a single cluster center. At this point of bifurcation, what's happening is that that's splitting into two clusters. So this is really becoming this and then this. And then eventually they can't start splitting apart. So what we're going to say is that we're going to construct from any one cluster two new clusters where the vector describing this, or the vector describing the memberships for this is basically the original cluster, PTX, plus some epsilon perturbation term. Okay? And let's say it's half this. And PT1 of x is going to be half PTX minus this epsilon perturbation. You want to do it this way to make sure the mass of your cluster is not really changed, but you've sort of moved them a little bit. Okay? And then you run your IIB again for this new clustering and see, do they collapse back together or not? So the idea is that you want to check, should I split my clusters at this point or not? And you do it by splitting them by teeny bit and saying, okay, does the clustering now pull them apart, or does it push them back together again? And if it pulls them apart, you're at that critical point where, in fact, it was a good thing to pull them apart. So you can do this over and over and over again, and you get a different algorithm that allows you essentially to traverse for different values. So you can, and then you increase beta by a little bit, do this again, increase beta by a little bit, do this again, and you can now find sort of essentially a hierarchical clustering primitive. Okay? So this is called the DIB, deterministic annealing algorithm. So we had the IIB algorithm, which was this one. Then we have DIB, which is this sort of explicit split. Okay. Of course, we had an EM-like algorithm. We had this kind of divisive algorithm. Life would not be complete if we didn't have an agglomerative algorithm. So you can think of an agglomerated version of the information model, like a bottom-up thing. How would that work? How would a bottom-up approach to doing information theory clustering work? How do you think? If someone said, to you, okay, I want to design a hierarchical algorithm, but I want it to be, merging.
We changed here.
Huh?
We put beta at the bottom. So we're putting more and more control.
So let's fix beta. We'll go back and fix beta.
But we want to control the space. We want to give more and more importance.
I know, what I'm saying is fix beta. I want to find a hierarchical clustering, bottom up. What do I do? How do you build a bottom-up clustering algorithm? What do you have to do? How has hierarchical clustering worked in the past when you've seen it bottom up? What do you do?
Join things together.
Good. How do you decide which two things to join together?
That's the tricky part.
In general, how do you do? So what I mean, not here, but in general, what do you do?
The closest.
Sorry?
Closest.
How do you define closest?
Euclidean distance.
Only Euclidean? Any distance, as long as you have metric. So you need some kind of distance between clusters as a rule to decide when two clusters should be merged. Once you have that, you can just run the whole machine, right? Take the two closest clusters, which have points to begin with, put them together. Take the next two, put them together. Take the next two closest, put them together, and you get the full tree.
But that's exactly optional information.
Sorry?
Mutual information between the clusters.
So it turns out you can actually write it very cleanly, right? In the following way. So roughly speaking, let's see. So what you say is that I want to merge two clusters, and I have to decide whether they're worth merging. And remember, I don't have a natural notion of distance. This is all information theory. But it turns out, just like last time I said, that you can think of the ITY as some kind of induced KL divergence from cluster centers to the overall center. You get an induced distance from here. Basically, you get two terms. You get a term that says, oh no, I merged them together, I have lost quality. So there's a quality term. And you say, oh good, I merged them together, I've gained space, I've reduced my space. So there's a space term. So you have to put these together in some form to capture the penalty involved, or the profit involved, in putting these two things together. And it turns out that you can read this off almost directly from that original optimization that we were doing here. Right? So it works out to something like this. So basically the cost of merging corresponds to a distance between the two cluster centers. Okay? So let's say minus beta times that, because that's the quality measure, plus a distance between the cluster descriptions. Well, in terms of how let me say this distance between T1 and T2 in terms of X. So in terms of Y, in terms of X. So in other words, if the clusters are far apart in terms of Y, you don't want to put them, you lose quality. So you're unhappy about that. If they're close in terms of X, you're happy, so you put them together. Because they're very similar. They're expressing the same conditional memberships. So you can write this more formally. This actually becomes what is called the Jensen-Shannon divergence, and I'll explain that in a second, between the vectors in terms of X, PT1X and PT2X. And this becomes the Jensen-Shannon divergence of PT1Y, PYT1. PYT2. And of course, you should be asking me right now, what the heck is this Jensen-Shannon divergence? Where did this come from? It's basically like the KL divergence. And if you have 2 points in a space, I've said the KL divergence is this kind of weird asymmetric measure between them. The Jensen-Shannon is a symmetrized version of this, and it says, take the midpoint of these 2 points, measure the average KL distance to the midpoint. That's sort of like the Jensen-Shannon divergence, like the radius of the cluster connecting these 2 points. So formally, the Jensen-Shannon distance between 2 distributions is equal to the average of the KL distance to the midpoint, which is the average of the 2. So it's the KL divergence from P to P plus Q over 2 plus the KL divergence of Q to P plus Q over 2. Now in Euclidean space, it's just distance to the center, right? But here you have to say this more complicated. So in other words, you can actually capture the idea of merging information theoretically using a distance. Again, this sort of emergent distance in terms of the KL divergence. So once I have that, I'm done, essentially. Because now I have a distance function, I have a rule for how to merge. Find the things that are the smallest value of this, put them together. Find them, and so on. And this is called the AIB, the agglomerative idea. So again, I want to point out that it's very easy to take something and make it hierarchical, just by observing that you just need an oracle that tells you how close 2 clusters are. Once you have that, everything's done. In this case, because the mathematics works out nicely, you can actually express this very compactly just in terms of those 2 clusters. You don't have to look at any other stuff. So it becomes very efficient. I mean, as efficient as hierarchical clustering. Okay. Any questions? Before I move on. Yeah.
How do you choose which one to use? You have 3 options.
They have different options. So, for example, if you just want to find A clustering, you're not going to futz with beta. Then the AIB and the IIB are relatively decent. I mean, I've used both of them. They work pretty well. There's a more sequential version of this that works slightly differently. That sort of takes out a point, decides where. So it takes a random clustering, takes a point out, and decides where it really should be going, and then runs this over and over again. That also works well. But if you actually want to navigate the landscape, you need something like this to be sort of build up the whole landscape. So that it really depends on your situation. But one of this or that will work fine. Right? So I mean, like this one.
Do people often use this?
Often. It's not anywhere near as popular as, say, Kmeans or spectral clustering. But there have been places, especially in the world of text, where this has been used. In fact, you could think of IIB, or the IB method, as a precursor to LDA. There's in some sense, LDA, which we'll talk about later on in the course, latent dirichlet allocation, is a method it's a non-parametric approach to clustering that you can think of as a Bayesian version of this. You want to run something like this, but you put a Bayesian prior to do the appropriate Bayesian inference and get the result you want. So, but there's a class of algorithms, and also something called PLSI, probabilistic latent semantic indexing. They all come under this category. So again, they all come up for text. So that's kind of where they come from. So because text, you don't want to shoehorn text into some kind of weird Euclidean cosine similarity thing, and so this becomes more convenient.
Because I really like the formulation. It's very
So I would say that one place where you can see signs that you might want to use this is A, heterogeneous data. B, if your data is sort of naturally probabilistic, right? When you're dealing with word vector document models, right? It's very natural to think of a distribution of our words in a document. And when you start doing things like that, you're living in a space of distributions, then this becomes much more attractive. Because I don't need to impose additional structural assumptions on the space. I can just live with the distributions, everything works fine. But if I have other metric structure on the space, then you want to think about whether this is the right thing for you. This is kind of like a very abstract formulation that works when you don't know much else about the data. Or when the data is of the form where they're so different that the only common language is information theory. Right? And that's one of the good places to use this. So that's, I think, the best answer to when people do this. So it's not used everywhere. In most cases, you can impose some metric structure. But if you don't want to or you can't, and it's more naturally probabilistic, use this. Yes?
Is this related to BIC?
there's a type mismatch. I mean, BIC I think of as a way to test for the right number of clusters. So in what sense do you say this is related?
Oh, I'm asking you if there is a relationship between the two.
Right, but I'm not sure how. Okay, so.
I mean, I guess the same principle at play.
Oh, I see the information theoretic principle at play.
Right.
In that sense, I would say not exactly, mainly because both AIC and BIC assume some kind of likelihood model and then optimize based on that. This is trying to avoid even those considerations. So it's supposed to be purely information theoretic. I think if you went to LDA, then I think that conversation might be worth having there at that point. Because that's when they're both Bayesian ways of thinking about the world, and they both put certain priors, and then you can talk about it more evenly. Yeah, this is trying to be a very assumption-free model.
That's true.
Yeah, and in fact, this first came up in the NLP world, in the text processing world. And it's been used very successfully to model sort of neuronal signals and to model sort of, you look at two different spike trains in the brain and you want to say, okay, how similar are these neurons? You build some kind of distribution over spikes and you do things like this. So some of the people who made this method have been very successful at applying this to understanding brain signals. Another place where there's no natural metric structure as such, but you look at frequencies and you look at distributions. Okay. That's all I want to say about information theoretic clustering, but it's not all I want to say about compression-based clustering. So if we have no more questions, I'm going to sort of change topics now to one last bit. I won't spend too much time on it, just for the rest of the lecture, but it takes the idea of clustering by compression one step even further beyond this. Okay. So are we all good on this for now? So when I come and quiz you next week, you'll know everything. The premise behind these methods, the information theoretic methods, was to say that somehow we want to capture the idea of clustering as compression. That if you have structure in your data, you should be able to compress it down to that structure. That the data can be expressed in terms of the structure. The structure is more compact. Right? And that you don't lose any fidelity in the process of using. And again, I want to emphasize, this is a very different way of thinking about clustering than everything we've seen so far. This is everything else you've seen has been either in terms of distances or similarities or distributions and likelihoods. This is in terms of compression. And we argued that the information theoretic viewpoint is the right viewpoint to think about compression because it has natural notions like entropy and mutual information that allow us to talk about space in a principled, sort of systematic way. And that's all true, except for one problem. Consider a number. All right, a number. It's going to be okay. This is I'll claim a random string. I don't know if it's truly random. I don't think humans are capable of writing actually random strings. Let's say it's random. Let me write another string. Anyone go any further? Huh? Thank you. Keep going. Are you done? that's three more than I could do. Anyone else want to go any further? Huh?
8. 7 would be okay.
Which one? 7.5? Okay.
9.
9 is guessing. Blue 9?
No.
Okay. Okay.
7, 9.
Oh, 7, 9. Okay.
No, I mean 8, 9.
8, 9.
8, 9, 7.
7?
9.
I'm very impressed with two of you, so yes.
9.
Again, 9? Like, how could I have forgotten the 15th digit of pi? It's terrible. Okay, I think we get the point. If I had to ask you, the likelihood of seeing any particular digit, there's enough statistical tests out there to say that if there's some small error, it's going to be random. But the next digit is, if you squint at it, is roughly there's 1/10 probability of seeing any particular digit. Not quite, but Same thing is true here. one over two probability of seeing an issue next. These are both random, they're both random in that sense. But there's a different sense in which this is way more random than this. In the sense that while I still cannot predict the next bit, and in that sense they're both unpredictable, this is much more easily compressible because I can write as pi. In fact, if you want, I can write down a closed form expression for pi. I can do various kinds of things for pi. Right? It ends up being this long thing, but I know what it is. Whereas this, if I had to describe this, its description is itself. There's nothing else I can say about it. Right? Except that I have to toss a random coin. But that random coin, again, how to, so there's no other way to describe it except by describing itself. Whereas here, I have a much more compact. So while they are both random in terms of their predictability, so they're both unpredictable, they are not both random in the same way in terms of compressibility. And in a sense, it is very hard to talk about randomness of a single string. It's one thing to talk about a random variable, an ensemble of strings, and randomness with respect to the ensemble. How do you talk about randomness of a single string? The point where information theory diverges from what we really care about is this distinction between predictability and compressibility. Right? All our notions of entropy and mutual information and channel capacity and channel prediction are about prediction. Right? Can I predict the next bit? And if I can't predict the next bit, there's a lot of noise in the system. There's a lot of entropy in the system. There's a lot of information. But as we're seeing here, there's prediction, there's prediction. Right? I mean, it might look random, but actually if I knew the description of pi, I can compute the next bit. Forget about prediction. I know exactly what's going to be. How do we, if we really believed, if we've said all along that we want to capture the notion of clustering as a way to compress things, shouldn't we be using a different notion of compressibility than randomness? I mean, information theory has proven to be very effective and a very rich language to talk about it in one form. But there's clearly something that is different that we could be saying. And this idea of compressibility directly of a string gets us to the notion of Kolmogorov complexity. Kolmogorov, not Kolmogorov. And of course, this is the Kolmogorov here is Andrei Kolmogorov, the famous probabilist, who sort of basically invented the modern foundations of probability theory. So he's famous for many things. This is just one of them. Okay. And what is the idea of Kolmogorov? If we talk about compressibility in terms of description length, how many of you heard of MDL? A little bit. So MDL is called minimum description length. It's a technique for describing things. If we want to say that we're going to express the space, not in terms of the number of bits needed to describe it, but in terms of the number of bits needed to describe it in a different way, here's what we might say. We might say that the compressibility or the Kolmogorov complexity of a string, which I'll write as K of S, okay, is the length of the smallest program that generates S. So think of some program that takes a null input and its output is S. So for example, the program could be, we'll do some Python. F of X. This is a program. We can count the number of bits required to write this down. Right? Its length is going to be the length of X plus some extra stuff. Right? So of course I want the smallest program. This is one program. So the Kolmogorov complexity of S is always going to be less than or equal to the length of S plus some constant depending on the language. Right? So I can fix the language, and I can say, write me a program in the language that outputs X and give me the smallest such program. You can think of the exercise in good compilers. Find a good compiler. I can really compile this down to the smallest thing that does the job for you. Right? This is the Kolmogorov complexity of a string. The problem is that this is a very tricky notion. And to illustrate a tricky notion, I'm going to write down a sentence. And the sentence I'm going to write down is, I want to describe a number. It's a very special number. Right? And the special number I'm going to write down is so this is my description of a number,
The smallest one?
positive integer, that cannot be described in less than 20 words. It's a program, it's a description of a number. We're talking about descriptions, right? So the description of a number. Can anyone see the problem with this?
This is so ambiguous.
Is it?
Yeah.
Why?
What? Look, you can describe a number in many different ways.
Sure, but this is a description.
Yeah, but it cannot. It may not be in English. It may be.
I think you're missing the point. There's a bigger problem with this. So this description is describing a word, describing the smallest positive integer that cannot be described in less than 20 words. How many words is this description? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I just described the smallest word that cannot be described in less than 20 words using 13 words. You see the paradox? This is called Berry's paradox. The problem is, like all problems in logic, when you start trying to describe yourself using your own language, you get into trouble. I'm trying to describe a number in its own language. If you ever bump into Mr. Girdle, you should know this is a bad, bad idea. Bad things are going to happen to people who try to eat their own tails. And so, what this basically is saying is that suppose I had a program that could actually do this. Suppose I had a function that could generate the length of the smallest program. Okay? Then I would have a contradiction. Basically by using various paradox. In particular, here, I'm going to generate a program. So, this is sort of Python pseudocode, so don't yell at me, it's not true Python.
We need a colon after your while.
I said. Jeez. Fine. Okay, so I actually wrote this thing out on my laptop and counted the number of bits in the ASCII form of expression. It is, if you trust me with this, it has 952 bits in it. Okay, so this program has 952 bits. Okay, and let's assume that this magic program here that computes Kolmogorov complexity has 100,000 bits in it. Okay, it's actually 100,000 bit long thing. So what is this going to do? This is going to generate, so think of this as a formal version of Berry's paradox. This is a program, right, of length 100,952. That's going to generate a string of claimed Kolmogorov complexity 100,100, which is a contradiction because I just produced a program which is shorter. that can describe that string. It cannot have that complexity. And you can keep doing this over and over again. Okay, so in other words, think of this, this is basically the same version. This is a formal expression of Brady's pattern. In other words, the Kolmogorov complexity of a string is undecidable in a formal sense, in the sense of halting problem, undecidable. It's undecidable. You cannot consider it. It does not seem like the best basis to define a clustering algorithm.
Yeah, exactly.
Nevertheless, as a rule of thumb, and if you're a theoretician, you know this, the minute you see Kolmogorov, you should think undecidable. Almost anything to do with Kolmogorov complexity is undecidable. There are very few things that aren't. There's a whole notion of time-bounded Kolmogorov complexity, which is a bit better. But it's a very powerful notion, and you can use it to prove many theorems by reasoning with Kolmogorov complexity, but I won't get to that. Okay, so you define a notion of compressibility, and this notion of compressibility is undecidable. We sort of, derails our whole plan of action with the first step. Because anything we do like, we like our algorithms. We don't like them to be impossible to do. Right? So what do we do here? Well, it turns out that you can get essentially an approximation of this. If you think of Kolmogorov complexity as the length of smallest program generating S, you can sort of think about compressing S down to the smallest possible thing. And if any of you have ever used gzip or lemple zip compression in general, right, you know that what it produces is not a compressed string. It actually produces a program. Because it says, oh, okay, here's a pattern. Go back and look at that part of the pattern over again. Go back and look at that other part of the pattern over again. In fact, to decrypt, to decompress a string, you have to actually run the program encoded in the bits. So things like lemple zip compression, which are in the limit optimal, are actually giving you a program to generate the string. They're not giving you sort of, that's what the output is. Okay? So you can actually say that rather than trying to define the Kolmogorov complexity of a string, which is undecidable, I can imagine some kind of reference compressor. I have some compression algorithm, which takes a string and outputs some compressed version of it. And I can define all my complexities in terms of this compressor. And so you can do things like, what is the ability to compress one string given that I have another string, and so on and so forth. You can define things like the equivalent of conditional entropy. Right? Conditional entropy is basically what? It's the amount of entropy left in a system after I've given you some other information. Right? You can write it as h of xy minus h of y. Similarly, you can talk about the conditional information of x given y as the size of the compression of xy minus the size of the compression of x. So in other words, take a string, compress it, look at the size. Take two strings, concatenate them, compress it, look at the size. Take the difference, in some sense this is the extra amount of bits you need to compress x once you're given y. Because if y is, for example, a duplicate of x, then c of x given y is going to be nothing. There's going to be nothing left over. In fact, you could say that c of x is going to be basically c of x. Maybe some constant x. So you can actually write down a collection of axioms that you would like your compressor function to satisfy. Things like, properties you want that compressor of x should be less than or equal to the size of x. You're compressing after all. Plus some constant maybe. The compression of xx should be roughly the same as x. Compression of xy, and this is a little bit trickier, and there's some reasons why you need to say it this way, should be less than or equal to, of course, cx plus cy, but you might need some extra fudge factor because you have to somewhat distinguish x and y in the string itself, so maybe some extra log term here, which I will not talk about. Okay? And then finally, what is called a distributor property, that cxy, the compression of xy plus the compression of z, is less than or equal to cxz plus cy. Okay? So think of this as z distributing over x and y. And something very cool happens once you have a compressor that satisfies these axioms. Once you have a compression method that can satisfy these properties, you can now define a distance between strings. So the distance between strings now is going to be the following. Again, we want it to be something that's small if they're similar and large if they're far apart. So I'm going to say it looks like this. C of xy minus the min of Cx and Cy. Right? Think of this like the conditional entropy, right? The amount of difference I have, normalized by the maximum, because you want the number to be between 0 and 1. Okay? And the beautiful thing is that you can show that any compressor that satisfies these axioms will give you a metric. So it's triangle equality will be satisfied, symmetry, all the usuals. So what have I done with this? What I'm saying is that I now not only don't have information theory at my disposal, I have nothing. All I have is a compression technique. So I brought this whole issue down, of clustering down to basic terms. I have an oracle that compresses, that's all I have. And it could be gzip. In fact, in practice, people just use gzip. And it has these properties. Once I have that, I can define a distance function between strings, completely based on the compressibility idea. Okay? So in fact, I was trying this today morning, right? I was just playing with this. And on my laptop, I have all my notes from my various lectures, all the scribbles that you see on these papers here. So I took, so basically you do exactly what this says. So, I took the lecture for today, and I compressed it using gzip. And the compression size was, once I compressed it, so the compression of the IB lecture today was these many bytes. Then I removed one line from it, the top line, and I compressed it again. And this was something like, it was slightly less. I saved 4 bytes. Okay. Then I said, okay, what I need to do is concatenate the 2 lectures and compress that. So I compressed IB prime, literally just by doing cat and then compressing it. And what I got was 3229. Just put that in there, all these numbers. You get the distance between the 2 lectures. It's something like 0.029. And there's a number between 0 and 1, so it's already calibrated. I did the same thing with 2 different lectures. I had a lecture from previously on choosing k, and I did exactly the same thing on that. And the distance I got for those 2, in IB and choosing k, was something like 0.91. So think of what I just did. I took 2 arbitrary collections of text. I didn't do TF, IDF, I didn't do anything else. I just trusted gzip to do magic for me. And out of that, I produced a distance function. And of course, now you can imagine, okay, once I have a distance function, can I run a clustering algorithm? Yes, what can you run? If I have a metric, what can I do? Like what? Anything? Can I run Kmeans? What can I run?
Hack.
You can run hack, you can run K-center, you can do K-median, you can do all kinds of stuff. All based on just having a compressor. So if you thought that information theoretic approach was kind of powerful, this is something that's even more powerful in the sense that it can capture anything you might have. Now again, because it's so general, it's not going to be as high fidelity as maybe something that's more careful. But it does say that if I have data that I have no clue what to do with, and all I have is some kind of text that I can run gzip on, or some other compressor, not even gzip, maybe I have some other way of compressing the data. I can define a distance function, I can prove that it will be a metric, and it actually makes sense in a Kolmogorov complexity method. I think that's very interesting. It's not, by any means, they are not very popular methods for doing clustering. I think also because they're not so well known. But I think they do represent a very different way of thinking about what it means to cluster. That's really what we're after here. Right? The semantics of what we want to cluster.
Yeah, but the hard thing is here, getting a good compressor.
Yes, and that's why I said, we just use gzip, which is as good as compressor you're going to find anyway. Or whatever you want, bzip or whatever
Yeah,
you
but
want.
what if the only thing that they give you is a word, a single word?
You can compress a word. It doesn't compress very well, but
Yeah, we can imagine the distances between words.
yeah, but think about it this way, right? If I have a word and I have another word, you're going to actually be able to tell the difference. I mean, they're going to be very similar to each other because gzip is going to realize, oh, wait a second, I have a prefix here that I can use. You're going to get a very small number here. So even if you just have words, you're going to find stuff there. There's no semantics. I mean, the fact that these 2 words are very different in semantic land is going to be completely ignored, and that's fine. I'm not saying that it will capture all of that, but it does give you something.
Okay, so here's one thing. So let's say we have the input is a word.
Yeah.
For a given word, we know in what let's say what sentences this word appears.
What's the
what's the
case?
context of
The
this?
context, okay, yeah,
And then we take another word.
yeah.
And we again print out all the context.
Yes.
Then we compress it.
Yes, you could do that.
So what do you expect? They think we're gonna get good things?
Well, I think you will get your context for this word will be a text document. Your context for this will be another text document. You'll compress them and you'll get something quite different. So you could, in fact, do this.
Yeah, I think it's a very interesting experiment.
Yeah. I mean, yeah, exactly.
Is there a sense in which things get clustered using this method? Is it so generic that it's hard to say what this clustering captures?
I think all you can really say is that it's relying. The compressor has the magic. Whatever the compressor is finding as structure, it's clustering based on that.
I see.
So if you use gzip, it's looking for text patterns.
So in my
So yeah, so I think what you're doing is you're deferring all those questions to what C does for you.
So in my example, right, basically, if two words are similar, you would expect that they appear in similar contexts.
Yeah.
Therefore, the gzip versions of them should be
Should be
good.
good. Yes. Yeah, you could try it. I've not tried this, but I think it'd be cool to try. Some of the people
But
who worked on this have used this, for example, for biological data and for signals and things like that. Couldn't come up with an metric easily. So they said, I will just run
But the
it.
problem is that you have only numbers in the compressions. So the output.
You only what?
you have
Numbers.
Only numbers. The
Yes,
number
because you
of
want a
bytes.
distance function.
So this is then not good.
Well, you don't get features, so that's what you're asking. Is that what you're saying? You don't get a feature representation.
Yeah.
But.
You have the text file.
No, wait. Suppose I have a bunch of objects, and all I have is a distance function on them. So I get a matrix of distances. Is there not a way to convert this into a feature map?
Sorry, can you repeat?
All I have is a matrix of distances. There are ways to convert this into a feature map. You can do embeddings of various kinds. You can do spectral mappings. There are all kinds of things you can do with that. So it's not as if all hope is lost. You could imagine constructing features that give you exactly what the compressor is doing by taking the distance matrix and doing MDS or something else. Right? Again, so again, that would be a very weird thing to try, but you could do it because once you got the metric, then you got something. You got a structure. That's the point. The compressor is giving you some geometry to play with. It's a very weak geometry, and that's fine because compression is very abstract. But it's something. And that's the benefit of this whole clustering as compression, that it can be used where nothing else can go. Any questions? Okay, all right, if we're done for today then. See you next week.